Good evening, everybody. Welcome to the third installment of our webinar series on engineering a touring tiny house. The reason that we're doing this is, number one, we're building a tiny house. It's called the Tiny Lab, as you can see a picture of it there in the bottom right. And also because even though everybody's talking about design of tiny houses and cool sink ideas and flooring and space-saving ideas, etc., and even potentially how to insulate and air seal, which is what we talked about last week, very few people are having a conversation about engineering of the systems of these houses. And what's really cool to me, as somebody who is a doctor for houses, is that all of the things that go wrong and go right in big houses are much, much clearer to see in a tiny house. So that's why we're going to be using the tiny house in the way that we are. And today we're talking about heating, cooling, and ventilation, as always. If you have questions, and as you have questions, I hope that you do type them into your questions pane, which is inside the GoToMeeting control panel there. I want you to do that, number one, because it would help for you not to forget your question at the end. Number two, I'm not going to take questions until the very end so that we can blast through all this stuff, try and get it in. I'm going to try and stick to a half an hour this week, even though last week we went to almost an hour. So I'm going to take all the questions at the end, and I'm fine to review over things that are even I'm talking about right now at the very, very beginning. So please do just type those in, that we don't have to remember them, and I can hit the ground running when we have questions when they do come along. You can see a picture of my beautiful, lovely wife there on the photo. She is not with me tonight, and even though we've been married for 11 years now, I'm terrible at doing an impersonation of her, so I'm not even going to pretend. She's not here. She wasn't able to be here tonight. She sends her regards to all of you, so thank you guys very much for taking the time tonight. All right, let's get to it. First of all, we are in number 3. Number 1 was all about the shape and the layout of our tiny house, and the reason that we chose the layout and the shape of the house. So if you didn't see that already, you can see that on our website at buildingperformanceworkshop.com, and I'll flash that up in a minute. And the second one, which was last week, was on the insulation, air sealing, and weather barriers. That one was really, we took a lot of time getting into things. So as you know, I'm a talkative person, and I have lots and lots of information to give out. We work on these kinds of buildings, but much, much bigger for our living. So that's why we're so interested in helping everybody get the right information about the tiny house. Now, if you want more information, every single month in and month out, for free, I offer a mastermind series. It's called the Building Forensics Mastermind Series. It's open to anyone. It's only limited to 100 people, so feel free to come anytime. It's the first Wednesday of every month at 1 p.m. Central. And you can sign up for months in advance, and GoTo will remind you the day before, hey, don't forget we've got that webinar tomorrow. So anyway, that's always there, and it outlines a job or a series of jobs that I had in the past month. And this is showing how this stuff works in real homes all over the place. So you can sign up for that at buildingperformanceworkshop.com. If you want even more and you want to become a ninja at this stuff, I have my Fall Fast Track. And the Fall Fast Track is special right now because it's enrolling right now. It only happens once a year. If you know any contractors or people in the building industry, and that includes architects and engineers and inspectors and even people who want to be really excellent homeowners, take this class. So this is for the black belts of home performance, and home performance is the cream of the crop of the residential construction industry. Anybody who is at the top uses the diagnostics, and that's what I specialize in. So you can check out more of that at buildingperformanceworkshop.com. Again, now let's go ahead and rock this thing. So we're using this tiny house to go to 16 cities in 2016. So we needed it to be aerodynamic, we needed it to be fuel efficient, we needed it to be stand up to the earthquakes and hurricanes at the same time that it's going to go through every time we put it on the road. So the Proof is Possible tour is a crowd-sourced tour. This is something that's really kind of strange. It's not like crowdfunding. We're not saying, here's what we want to do, give us money. We're saying, here's what we're going to do in any city that we visit. Now, you tell us, fans, what cities you want us to go to, and our fans will buy the cities. So right now we're already looking at Dallas, Austin, Cincinnati, Sacramento, San Diego. We're looking at a whole list of places that are super cool and we're excited to visit. If you want your city to be on that list, feel free to get in touch, or get in touch with somebody in your area that wants to differentiate themselves and prove that they're better than everybody else in the construction industry. So cities are bought, like I said, and the campaign runs from October 19th through Thanksgiving. By Thanksgiving, we will know everywhere where we're going, and we'll start to schedule it. So you can find out more about that at prooфispossible.com, and that's where you can actually see this tiny house in person. So real quick review. Because this is important, everything that I'm going to talk about has to do with this 4-3-2-1 way of looking at things. I came up with this way of teaching home performance because I'm a dummy. And everybody raise your right hand right now. Let's all do this. Okay. Beginning of a webinar. Repeat after me. You're raising your right hand. Repeat after me. Sometimes I am an idiot. Okay, good. So now we're all on the same page. I don't think very clearly when I'm trying to juggle a whole bunch of stuff in my head. So when I'm inside somebody's house and I'm thinking about all these different things, I like to remember that there are 4 ingredients to home performance. There's heat flow, airflow and pressure, moisture, and indoor air quality. The most important end of my list is toward the right. So heat flow and airflow and pressure are the least important, and that is what energy efficiency makes up. So energy efficiency is not what we're talking about. We're talking about performance, which is much bigger. There are 3 improvements that I would always make to any home, whether it's brand new, being planned, hasn't even broken ground yet, or an existing home that's older. And that's air sealing first, insulation second, and then HVAC stuff third and lastly. If you don't hit the air sealing insulation, it doesn't matter what HVAC stuff you do, it's not going to work. The 2 systems that we're always talking about are the enclosure, which we talked about last week, and the engines, which is what we're talking about this week. And the goal of all of this stuff, where we analyze the 4 elements, we make our 3 improvements to our 2 systems, is control. It is not energy efficiency, it is not sustainability, it is not green, or even living in a very frugal and downsized way. It's always just control. If I want to live that way, can I do it? And the answer is yes, and that is because I have performance tested the house. And performance testing is the whole thing. It is not a part of it, it's the whole thing. So here's the layout, and we're going to get into the performance testing side of this thing. Just to remind you, bathroom at the front near the tongue. There will be a shed over that tongue that you'll see soon. The kitchen is right behind the bathroom as you move toward the back. And then we've got an under loft for sleeping. And the loft that's half elevated, just a half staircase up, is the dining area. And that's going to kind of transform. I'm really excited to show you guys the videos of when we're constructing this thing, which is going to start again in November. So the 2 systems are, we already talked about the enclosure, we're talking about the engines today. Engines in a house are anything that move heat or air or moisture. So let's take a look at this. We got this house over here. This is courtesy of Department of Energy. Thank you for illustrating this house for us. We have our air conditioner, which is on the outside. That's the condenser or compressor portion of our air conditioner. We have a fireplace. That counts. We have the air conditioning system that is inside, and that happens to be in the attic in this house. That's also part of our engines. We have our kitchen exhaust, or excuse me, our bathroom exhaust fan, as you can see there. We have our refrigerator. When you start really thinking about this stuff, what a refrigerator does is move heat from inside the refrigerator to outside the refrigerator. That means that everything around the refrigerator is going to be warm and everything inside is going to be cold. So that's kind of interesting. It's fun to think about this stuff. We have the basement systems. In this case, we got a water heater and a sealed combustion furnace. We have our kitchen range hood. We've got our dryer. All of these things really matter. And they all are going to have an impact on each other and on the conditions in the house. That's why home performance is such a big deal now. People think that it's new because it's a fad. It's not. It's new because we've been building houses differently than we ever have before. So here is what we need in this tiny house. In the tiny lab, we're going to need at the very minimum a heater. We are going to be traveling around the country. We're going to be trying to build our tour very smartly, and I'm going to tell you a little bit more about that in a second. But when we are done with it, we're going to relocate in Atlanta. And Atlanta does have cooling and dehumidification that needs to happen. You do need an air conditioner when you live in Atlanta, Georgia. But interestingly, Atlanta is actually heating dominated, so we're going to need more heat than we need cooling. Now that cooling slash dehumidification can be both. That's what an air conditioner does. Or we could just do the dehumidification. So we're going to talk about kind of what my mindset is on this. And by the way, this webinar is going to be a lot of questions and wish lists. I don't know what we're going to do yet because we are actually coming up against things that are stumping even the experts, like the world experts on this stuff. Number 3 is we need an exhaust fan. We need exhaust fans, multiple. I'll tell you why I'm using the singular here, because we're going to need to exhaust moisture from the shower and from the kitchen. Period. You always need to do that because those are two places where you're creating moisture, and also in the case of a kitchen, nasty gases that you don't want to be breathing, like carbon monoxide, for example. Number 4 is a fresh air ventilator, and this is separate from my exhaust fan. A lot of people will use the exhaust fan to provide the ventilation, and I will show you, in case you don't already know this, why that would be absolutely impossible in our case. And number 5, we need water heating and plumbing. I am married, and I want my wife to stay married to me, so I need water heat. And plumbing, obviously, right? So I'm not going to be swimming in lakes for my cleaning needs. So all this stuff is really interesting to me, and that's why I really wanted to make sure that we talked about this today. So first is, we need to do the manual J calculation. This is the first step in any HVAC upgrade or HVAC installation. It always needs to be done. And it looks like I did not write this by hand, right? This looks like it came from a computer. That's important because you always want to do a manual J in a computer. Manual J is a manual. It is an actual book that gives you a number of steps and rules to follow in order to run a calculation that will tell you exactly how much heating and cooling you need in a house. And this could be an apartment or a mansion, it doesn't matter. So I'm using this on my 190 square foot tiny house. So what you can see here is that number 1, we've got the square footage of room area is 173. That means it's subtracting out the wall cavities, which is kind of interesting. By the way, just to reiterate, as you have questions, type them into the questions pane. I will take all questions at the end just because I want to make sure that we don't hold up. This is going to be recorded and in video format on our YouTube channel, so I will get to your questions. Also, if you would like to speak, just raise your hand at the end of the webinar and I will unmute you. So, we have 173 square feet of room area. We have shy of 2,000 cubic feet of conditioned space. And we're going to be building in about 928 square feet of living area per ton of air conditioning. That's actually not super great. A lot of my clients that I help plan this stuff for are getting up to 1,1600 square feet per ton. That means if I live in a 2,000 square foot house, I would only need a ton and a half air conditioner. A lot of people who live in a 2,000 square foot house have a 2, 3, 4-ton air conditioner. And that's because whoever installed it did not do this step. Do not assume that this happened. Now you can see the building loads here, which are in BTUs per hour. I'm going to get more into that in a second. But aside from all of these numbers, which are not fun to look at, you also get fun graphs that'll show you where your biggest opportunities for improvement are. You will also get pie charts, which I love, and you will even get timed out tracking of the heat load and the cooling load. This is really cool because the reason that you do it in a computer is that you're able to analyze the heating and cooling needs for 8,760 hours in the year. Every single hour throughout the year in your climate zone is calculated. That's what's awesome. So we're going to use this information to figure out what we're going to do about heating. So the heater has a couple of things about it. First of all, obviously we did that calculation. You just saw it. In this case, the manual J is very, very sensitive because I've got such a small space. It is less than 200 square feet total. By the way, I'm doing a block load, not a room by room calculation because I've got just basically one giant room. Now the fridge, as I mentioned a few minutes ago, right, everything outside the fridge is going to be warmed and everything inside the fridge is going to be cooled. That means that if I model in my calculation that I've got a normal sized fridge, my calculation is going to think that my fridge is going to be providing a whole lot of heat to my house. And in fact, I'm going to have a tiny little fridge that's like an RV style fridge that'll produce almost no heat whatsoever. So my calculation needs to be configured for that. And that's why you always work, even if you're going to do this yourself, if you're a homeowner that's like super awesome, and I have plenty of clients who worked at NASA or are engineers and want to do this stuff themselves, it's great. Have somebody who really knows what they're doing help you with it, at least look over it and just consult for you. Now we're going to compare this to the energy model. Now a lot of things that you'll see in tiny houses, heating-wise, are on the left. We have a pellet stove. In the middle, we have a little marine heater. and that's propane fueled. And on the right, we have a wood burning stove. A lot of people in tiny homes, because they want to live simply, and I'm making quotation marks, will go out and chop their own wood and burn it in their fireplace. Now, here is why this is not going to work. First of all, I have analyzed the energy model, which we looked at last week, and we found out that our above-grade walls were our biggest problem. The Manual J also thinks that the above-grade walls are the biggest problem. That's fine with me, because the above-grade walls, and that means the walls, it's just another way of saying not basement walls, the walls are the biggest part of my house. I have a one-story house with a little roof and a little floor, and the walls are huge, right? So that is the biggest part of my house. That's fine. That looks normal to me. Now, you can see in the pie chart also what's going on here. The walls are the biggest weakness, and it agrees. Both of those things are good. Now, which one of these things, the pellet stove, the fireplace, or the small heater, or even the electric, right, is which one am I going to have to choose? First of all, we have, as you can see in this pie chart that I just flashed up here for you, we've got a building loss, and that's what's called the heat load. That's like the junk that the house is carrying. That's all of the ways that the heat leaves the house that I need to then bring an engine into the house to produce it to replace what just got lost. 4,000 BTUs per hour. Every hour I'm going to need 4,000 at the coldest day possible. So that's 4,000 on the coldest. That means it's going to be less than that every other day of the year. A lot of days it's going to be 50 degrees out, not 0 degrees or whatever I'm designing for Atlanta. That means that I'm going to need a lot less. Now, pellet stoves will go from 8,000 BTUs per hour up to like 90,000, 120,000. That's too big. That is way, way too big. That's going to give me twice as much heat as my house needs in any given hour. What that means, practically speaking, and if you live in a tiny house and you would like to comment on this, and you use one of these, I would love to hear from you. But what that means is that as soon as I turn this on, within 15 minutes, it's going to be pretty toasty in there. And remember that a fireplace needs to build up, needs to actually like be burning pretty well to be at efficiency. So I'm going to open a window. And now I have completely gotten rid of all the other performance things that I was designing into this, where I'm air sealing and insulating. Once I have a fireplace and an open window, everything is out the window. Literally. It's literally out the window and up the chimney. So I am not going to do a fireplace, especially not a ventless fireplace, because, by the way, those produce carbon monoxide, period. They do. And the dirtier they get, the more dust gets on them, and the burners I'm talking about, the more carbon monoxide they'll produce. So in such a tiny space, you do not want any carbon monoxide. So do not do that, period. So we're going to have to stick with a marine heater. And remember also, we're not doing electric. Electric was not on my list at all because we need off-grid. We need to be able to park wherever we want, whenever we want. That's part of the life that I want to live here. So while we're on tour, at least. So we can't do electric because electric heating is the most inefficient way to heat anything, period. It's like a toaster. So we've got two different marine heaters. These are both made by the same company. The one on the left, I actually tended to like better as far as the look. I thought it looked pretty cool and weird. The one on the right is a lot more popular with most tiny houses that you see. Now on low, both of these are about the same. They're going to be 3,200 BTUs per hour, and on high, 4,500. That is perfect for my window. I love it because 4,000 is right in the middle of that. So I can turn it down to low and on a slightly warmer day, and that would be great. Now, on the right, we've got what's called the P9000. That is the direct vent model. That is important because that means it's both exhausting its combustion gases to outside and bringing in fresh air to burn with from outside. So it actually has no connection with the inside of my house at all, and that is what I want, because on the left, that guy you can see at the bottom there, underneath the bottom of the canister looking thing, you can actually see the burner, and it's right out in the open. That means it's using air in the tiny house to burn with and then sending it up the chimney. And my tiny house, as you remember from last week, is super, super tight. So there's no possible way this thing is ever going to work. I'm going to have to replace it immediately because it's just going to keep on shutting off. So now we come to number 2, the cooling and dehumidification. Now over here on the right, you see what, in my mind, is happening with most of houses in the world, and especially tiny houses. Because we're just guessing. all the time. We're using equipment that's really not meant for this purpose to do these things with. Now let me show you this. The Manual J tells us that I need 2.2 kilobTUs per hour. That is a tiny, tiny air conditioner. Now remember, this is very touchy, right? Still. And the smallest window AC that I can buy is 5. That's more than double oversized. That's actually typical for my clients. Even with 5,000 square foot houses that I'm working with, they'll be double oversized what they actually need. I can't do that because it's really critical for people to understand that when you double oversize a piece of cooling equipment, part of, remember, the cooling's job is to dehumidify. And when I have double oversized it, I'm going to do the same thing as I did with the fireplace, except I will get it nice and cold in my tiny house, but I will not dry it out. And drying it is the big deal. I'm going to talk about that in a second. Now, the smallest window AC is 460 watts, and that's at steady state. I'm going to have a solar system that we're going to talk about next week. We are going to have a solar system. Grace will be here again next week. But our solar system is going to be 520 watts total. That means I can't run anything else basically when I've got this air conditioner running. That makes me PO'd, so I'm not going to do that. And remember, when it starts up, when that compressor starts up, it's going to draw even more energy, so that means that I might potentially be shorting out all over the place. And I don't know exactly how that happens, how it works with the solar system, but I know that it's going to draw more at the beginning. So our simple solution for cooling is to just let's go where the weather is nice. So if you think of a map of the United States, we're going to start in Tampa in March. We're going to follow the south border of the U.S. for until early summer, and then by early summer we'll be up California to the northwest, and then we'll be going through the north part of the country in the summertime. So we'll be always where it's going to be kind of reasonably warm/cool. So the cooling load, again, load, think about it. Your house is a car, and you have a trailer behind you full of junk. A lot of people will automatically think, wrongly, that, oh, in order to haul all this junk around, I'm going to need to buy a bigger car. And that's what people are doing when they buy a bigger air conditioner or a bigger furnace. The better idea is to get rid of the load, and the load is all of the things that are wrong with the enclosure of the house, so that you have to buy bigger engines to take care of it. All right, so we want to lower the load. The load in this case for summertime, this is the gains that are from the hot air outside and also the sun beating down on the house, are mostly the walls and the glass. That is a really good pie chart. I really like the shape of that one. A lot of times it'll be infiltration will be a big deal. And as we talked about last week, this house can be tight. So that's good. The roof is hardly anything at all, and that's because of what I have made the roof out of. And if you want to review that, the video is on the website. So we're talking about 2.2 kilobTUs per hour. Walls and windows, and remember that it's going to depend on which way I park my tiny house. A lot of people don't think about this. Even when they're building a house, especially when they're building a house that's like near mountains or a lake, you buy a lot and you're going to put the house so that all the windows point at whatever you want to look at. This is a major problem because here is what it looks like when I rotate my tiny house. So if I was to park with the front door facing south, that means that my tiny house directionally, if I was driving it, would be heading west. If I was to park it that way, that means that I'm going to be the most efficient possible. If I park it so that my front door is facing east, and that would mean that my tiny house is heading south, that would be the least efficient way to do this. And in fact, that adds about a quarter to a third of my total needed cooling capacity. So you can see that this curve is going to lead to something like this. This is a typical day in the summertime. This is August in Atlanta in this case. I can't model for every single house or every single town that we're going to pull into, but at 8 o'clock in the morning, I'm only going to need 2,100 kilobTUs of cooling if I park the way that I need to, so that's front door facing to the south. And at 1 o'clock in the afternoon, it's going to be as hot inside as it's ever going to be. I'm going to need 2,500 BTUs per hour of cooling to take that heat, that 2,500 gain, out of the house. And as it goes down until 7 o'clock at night when the sun goes down, obviously when the sun is down, there's no gain. So we don't have to worry about that. This is actually a really good curve. Have you ever seen a curve like this before? Generally, the high point is going to be at 4 o'clock or 5 o'clock in the afternoon. And that's because of this. What this 1 o'clock peak tells us is that the roof is the main way that sun is creating heat that's beaming into our house. Over here, you can see that there is this peak at 4 or 5 o'clock p.m. on this yellow line with purple squares and on the purple line with blue triangles. Those are parking the house so that the windows are heavily facing west. That would be bad. And in fact, that is where I'm adding 30% to my total cooling need. I'm going to need to buy a 30% bigger air conditioner in normal life. In this life that I'm living right now, which is tiny house life, there is no difference between 2200 and 3400 because they don't make either one of those sizes. I'm still going to have to buy a 5000, right? So this is where the conundrum really is coming in with trying to dial all this stuff in. The line that we're seeing on the left, which is the ideal line, looks really much more mountainous than it actually is. The one that you're seeing on the right, which is the red with purple triangles here, this is the line that we're seeing on the left. That is the most reasonable line on this chart. So what I always want to do is park it so that my front door faces south, period. That's always what I'm going to do. Now, here's what we would love to do. This is a ductless mini split. Now, ductless mini splits aren't like everybody's really excited about them. It's great. I'm really happy about that. But this is special. And I've been friends with these guys for a long time. This is Mitsubishi. These Mitsubishi ductless mini splits are being installed in Montana by themselves with no electric heat backup, and they are doing fine. And that's because we're dialing in everything just like we've talked about for the last 3 webinars here, and we'll do on the last one next week. This thing will go down to, on the low side, 1600 BTUs per hour of heat or cool, and that's good because that's also in my range. And to run either of those in cooling or heating, it only takes up on the low side 110 watts. That's much better than my 460 watt window air conditioner. That's super efficient, and I like that. So we're going to try to do this, especially because that is an infrared sensor that is embedded inside this. That thing is called a cartridge. It goes up on the wall, like high on the wall generally, and it's going to blow. The infrared sensor is going to see, let's see in the summertime, for example, I come in from outside and I'm super hot. I just got back from biking 10 miles and I'm steaming, right? I'm like, my body is 100 degrees and looks like I've got a fever. The air conditioner will look at the room and see me and say, oh my gosh, that is where we need to send this cooling. And it will direct all of the cooling to the hottest part of the room. I could just stay still and the air conditioner blows on me. In the wintertime, it'll notice where the cold spots are and it'll direct the heating to those cold spots. Isn't that amazing? Yes is the answer. So we love this, and we're going to really try to have one of these to show off when we're on the road. Now, keeping it dry is the bigger thing. This is the trick. The follow the weather thing that I was talking about, where we could very simply just go where the weather is nice, is fine if we're talking about temperature. But it is not fine if we're talking about humidity. Because what if it's 70 degrees every day, but it rains every day, and it follows us around the country, right? What this would mean is that, number one, we don't have a lot of materials inside, like couches and carpets and exposed wood and stuff like that, that's going to be able to absorb this. Drywall also. It's going to be able to absorb this like a sponge, the humidity in the air, and then when it gets dry again, give it back off into the living space. This happens actually all the time, and you should listen to, if you're interested in learning more about this, my most recent Building Performance podcast episode was an interview with the amazing Lou Harriman, who is the biggest expert that I've ever met on dehumidification. And he talks a lot about this kind of give and take that the materials in the air are doing with each other all the time. So we have to be able to capture the moisture in the air. Because if it rains for 3 weeks straight, all the air that's inside your house right now came from outside, of course. And that's why it's always really silly when they say, hey, the air quality is really bad outside today. Don't go outside. It's everywhere. Like, I'm sorry, but that's it's inside your house too. So here are some ideas that we came up with. Lou and I had a call earlier this week. I wanted to have him here to talk about it in person, but he wasn't able to. So number one, we have the possibility of like if you think about a bakery, you've got a refrigerator, a tiny, tiny little refrigerator that's sitting on the countertop, smaller even than an RV fridge. If we were to take the compressor from that and use it to just squeeze water out of the air, we could get by with probably less than what the Mitsubishi mini split will draw. And remember, since we're trying to go off grid, I care a lot about how many watts things are drawing. We could build a wall or build into the loft here that the dining booth sits on a block of desiccant material. This is like when you open up a package of shoes, you see the little silica gel packet in there. If we were to get a bunch of that, and in fact not silica but carbon is what was recommended to me by Lou, because carbon has this specific tolerance of up to 50% relative humidity. After 50% relative humidity, it starts absorbing water like crazy out of the air. And that's important because 50% is the high side of what I want my living space to be. It can absorb up to 60% of its body weight. I really like that. The third thing would be a chilled pillar. This was an idea that this amazing company called Transolar out of Europe did with a bathhouse. Now, I'm not planning on having a lot of humidity in this place, which is what we're going to talk about next with exhaust fans, but I do want to make sure that we definitely are able to capture liquid water. So here's the main way that we're going to prevent liquid water from becoming a problem aside from the rain issue. Number one, remember that our tiny lab is going to be 2 air changes per hour or less. That is 67 CFM. If I was to run a blower door test on this, and if you come and visit us on the tour, we will be doing blower door tests and all kinds of different tests on this tiny house to show how this all works. Do a blower door test to 50 pascals on my tiny lab, and you would hit 67 CFM. That means I'm going to have to basically take no rings out of my blower door, if you know how this works. If I was to follow code prescription, I would need to install a 50 CFM bath fan in a bathroom that has a shower in it. We are not going to do that, period, because that is almost like running a blower door on my house every single time I take a shower. That's totally insane. That's, by the way, about a 20-mile-an-hour wind on every surface of the house, floor, ceiling, and by the way, when we're talking about tiny house, we are really talking about every surface, floor included, right? So we need to exhaust the shower moisture, the stove moisture and carbon monoxide, the toilet odor, which we're going to talk about next week on how to take care of that, and the litter box odor because we have cats. So we're going to be exhausting from all these places, and here is how we are engineering this. I'm very excited about this part. We're going to have a central exhaust system. That on the left is called an inline fan. Some of you might have this in your house already. It would be positioned in the attic, probably. This happens to be outside. It's being used for radon exhaust in this picture on the left. But basically, we're going to take a whole bunch of little pipes, the diameter depending on how much air I want to suck from each individual area. The toilet and the litter box, a very, very small amount of air. All I need is air moving in the general area, in the direction of away. We want everything flowing away when it has to do with smells. Likewise with the shower and the kitchen. We don't need a whole lot if I can get it going in the right direction. And door placement, shower placement, kitchen hood placement is all going to play a huge role in this. And that's why we're going to be making videos like crazy when we're building this thing. I'm good at SketchUp, but not so good that I can build all this stuff into it so that you can visualize it well. So there's going to be 4 exhausts all tied into this one fan, and that fan is going to be able to be turned on and off. Now all the utilities are going to go in the front shed. Just to remind you, this shed is going to house the exhaust system, the propane tanks, because we don't want those kept inside, the solar batteries, and lastly, the water heater. This is all really good because I want that front space to be breathing easy. I want it to be not attached to my house. I want it to contain all of the things that are important to have near my house, but not inside. So all this stuff is going to be really useful to have inside this shed that's attached. And I'm using these quotes. Actually, Grace was laughing. We're going to have a shed and a garage. The garage is going to be the back of the truck, right? So, tiny house living. So the fresh air ventilator is number 4. Number 1, we need to remember that exhaust fans are going to need to be pressure equalized, because if I was really to run a 50 CFM exhaust fan in there, I'm going to depressurize the house like crazy. And if the door opens inward, I'm going to probably, if the door is not latched all the way closed, it's going to pull the door in, and it's going to open my front door every single time I turn on the exhaust fan. That's bad. So what I'm going to need is holes in my walls with weighted dampers on them to direct the air, so that when I turn on the exhaust fan, air starts moving out of the house, and of course, air is going to need to come into the house to replace it, and I want it to follow a very specific pathway. And mostly, since, thank goodness, we're located in the bathroom in this case, for most of the exhaust, we're going to not have to worry about condensation or weird moisture issues, because the bathroom is built to handle moisture. That's good. Now, we're not going to use these exhaust fans to provide the fresh air, because we're going to have a separate continuous system that is also balanced, but it's bringing in and out in very specific connections, in very specific equilibrium, rather. Both of which are forced. It's not like it's sucking and then there's a damper that's just going to open up a hole in the wall. So we're going to hit 20 CFM continuous all the time. Lou mentioned to me that if you were to provide 6 CFM to your nostrils directly, that would be a lot. That would probably be too much fresh air. So remember that we're talking about a very, very small place, and you want to use commensurately small and reasonable approaches. So this thing over here is an in and an out spot ERV, which I really like, and we're going to see about whether that's going to be what strategy exactly we're going to use here. So remember that in general, you can use one of 4 strategies. What we're doing is pulling stale air from the place that we make the most of it, and that's going to be, since we already have spot exhaust in the bathroom and in the kitchen, we're going to be exhausting out of the bedroom. And the little sleeping loft, we don't want that to get stale, because that would be bad. And we're going to push fresh air into the place that we're going to be bothered by at least coming in, especially if you're not using a recovery ventilator, which is what the RV stands for in HRV. That stands for heat recovery ventilator. It means that the air that's coming in is potentially not going to be exactly the same temperature as what is already in the room. It'll be slightly warmer or slightly cooler depending on the weather. So the 5th and last system that we're talking about is the water heater and the plumbing. As you notice over here on my diagram, the bathroom is at the very front and the kitchen is right behind that. That is by design. I don't have to run plumbing to the back of my trailer. It's all right there, which makes it super easy to install, super easy to run. I will have hot water immediately, because there's only about 10 feet of pipe between the water heater and me at the tap. So I really like that. We're going to use a tankless propane water heater. And tankless, not because tankless is inherently better. It is not. Tankless is good for certain uses, and in this case, it is perfect. Propane is important because off-grid is what we want. I can't use electricity because that will not allow me to be off-grid. Tankless is important because if I was to try and get a tank water heater, that would be a total nightmare. It would be like 40 gallons or 30 gallons minimum, and I don't need that much hot water. I need something that's small, that's light, and that's going to give me what I need when I need it. That's why we're going with the tankless. We will have water-wise as a reservoir, this blue square there that you can see underneath my kitchen is going to be the storage tank. That's going to be fillable at public bibs. Apparently, and I didn't know this until we asked around in the tiny house community, there are tons of places where you can get water in public at all like rest stops and at generally gas stations and et cetera, et cetera. There's just like millions of places to get this. I'm really excited about that. We're going to use PEX flexible piping for this. Now, lastly, we're just going to go over the real quick tips. First of all, remember that you always want to calculate. Everybody wants to sell you something. They generally want to sell you more of whatever it is that you need, right? You don't buy shoes that are bigger than you need. You buy the shoes that fit your feet perfectly and that are make you feel great. So do the same thing with your heating, your cooling, and your ventilation systems. Remember that oversizing is very easy to do. People might not do it on purpose. The reason that you run the manual J calculation, and remember that, write it down, is that it will help you to not do that. Lastly, remember to ventilate. You need to provide exhaust, and also you need to remember that air will need to come in to replace that exhaust, and where is that going to be coming from, and are we going to have pressure problems? I have the most recent Building Forensics Mastermind webinar was all about a client who had chimney smell in his house, and it was because we had too much exhaust ventilation, and the biggest opening in the house was the chimney, and so of course the house was breathing in through the chimney, which is the opposite of what we want. The contaminants, we're going to try and not bring contaminants in. We're going to try and, when we have contaminants, like for example carbon monoxide, moisture, things like that, we're going to be exhausting them right where we make them. That means you don't put the exhaust fan in your house over the toilet. You put it over the shower, and then you position the toilet so that air comes in to the bathroom and goes past the toilet in order to get to the exhaust fan where it then goes out. That's all really happy making. Now, I hope that you have enjoyed this. Remember, last week is the last week of this webinar series, and we're talking about the bells and whistles. We're talking about solar system. We're talking about our toilet. We're talking about the cat stuff. We're talking about the furniture, the mattress, all this stuff. And then remember that our crowdsource campaign is going to start on October 19th. You can check out more about that stuff at buildingperformanceworkshop.com. Now, I will take questions. Holy crap. Are you kidding? You guys have not been seeing my slides the whole time. All right. Well, let me tell you, first of all, I apologize profusely. Yes, this has been recorded. I will be answering your questions now regardless, and I'm going to send you all the video for this. So normally what I do, if you have been on my webinars, is say, please type into your questions pane that you can see my slides. I apologize that you have not been able to see a single freaking thing that I've done. That makes me a total idiot, which I am. And we said that at the beginning. So we already admitted it. I apologize profusely. That was totally dumb. And I've actually never done that before. Here's my last slide. You want to see that? Let me go to this freaking questions and see if there are any questions aside from whether or not you can see my slides. All right. Can't see the slides. All right. David says, you are touring many locations. What location did you use for the Manual J, and what seasons are you traveling? That's a great question, David. And again, I used Atlanta because that's where we're going to settle at the end. And also, you can't possibly imagine all of the scenarios that you're going to be in. So we're going to travel through the entire country, and I just basically said, you know what, we're going to stay with the warm weather. We'll try to be as temperate as possible. Follow that weather, right, is what I was talking about. So not to worry. I don't think that we'll be in too much trouble. All right. David says, the last slide looks great. Thank you, David. All right. Are we going, so Andrew wants to know, are we going to ACI in Cherry Hill, New Jersey? Is that next year, Andrew? I don't know if, I think that we're trying, we actually are in talks with ACI about trying to bring us to Austin in April. And that would be super cool because they want to bring the homeowners who aren't necessarily professionals into the conference. So hopefully that means that would work. But no, I'm not going to any conferences before this. I'm like slammed with stuff. Let's see. Joe says, I thought maybe you would use some sort of heat recovery from the AC to heat or preheat water from the tankless. That is an interesting thought, Joe. I have not considered. Are you talking about taking from like the compressor, the condenser coil? I think that's what you're saying. So basically Joe's saying you're dumping with an AC, you're taking heat from inside, dumping it outside. And if we were to take that outside heat and use it to preheat water, that would be kind of cool. I highly doubt, number one, we don't have a tank. And I think that's probably part of what we're talking about. We're not going to have a tank system, so we would have to heat the storage tank at large, which is actually inside the tiny house. And I don't want to necessarily add, especially in the season when we're using air conditioning, I don't want to add heat inside the tiny house. So I think that's a really cool idea, and I'll go ahead and let me know if there's something else specifically you're talking about that I am not getting, but I'll let that kind of wrangle around in my brain. Let's see. David says, "Come to New Mexico, new humidity." I love it. We are actually in talks with David. I hope that you and Hillary Ames know each other. David Wentling, meet Hillary Ames. You guys are both awesome. Hillary is trying to get us to come into Santa Fe, Taos, something like that. So why don't you guys connect if you want to put your heads together on getting somebody to sponsor it? That would be awesome. October 2015, Andrew, no, I will not be going to any. That's going to be in the midst of fall fast track, big time. Let's see here. David says, "Are you coming to EBA in October?" No, I'm not. Again, this fall is going to be crazy with busyness stuff. All right. So Joe says, "Yeah, you would need a separate tank, but free hot water. That is free. I like that. Although, you know what? This is actually a really good conversation to have because I am not necessarily that interested in saving money. Um, my goal with money in general, and I do not think I'm alone in this, is to not think about money ever. I want enough money to come in so that I can spend money when I feel like it, and I don't have to worry about managing my investments. I'm not worried about becoming a millionaire. I'm lucky that I have a wife who totally agrees with that. So we both just want to be able to spend money on things that we really love, and we'll go to a nice restaurant rather than a cheap restaurant just because I really want the high quality thing. So I think that the idea of like using specific strategies that would have uh, the primary factor would be saving money are totally outside my brain right now. And actually, I convince most of my clients to not think about that stuff too. All right, so I will be publishing this video, remember, on the YouTube channel. It'll be up in about an hour. So if you would like to come and just go through and you can just cursor through my slides, you'll be able to see everything that I was talking about. Again, apologize for the inconvenience there. That is ridiculous, and I've never even heard of anybody doing that. So I definitely beat the idiot standard on this one. David has one last comment. He says, "Consider air inlets for your exhaust system located over your bed area to bring in outdoor air, which would be cool at night." That would be true if it's cool at night. And I will think about that. But in Atlanta, for example, I don't want hot, humid air coming in at night. So yeah, but all of our brains now are like frizzling with these possibilities, right? So I really appreciate that you guys took the time, especially because you couldn't see anything. Have a wonderful night, and I will see you next week when you will be able to see stuff.